So hello, my name is Nicholas Bramhall, and this is my lab report for Lab 1. Alright, what is this lab and why are we doing it? The purpose of this lab is to evaluate the reliability of computational model when compared to real-world data, and we do that by observing a rolling object in constant velocity and then making a computational model of it. And we ultimately concluded that while there are some differences between the computational model and the real-world data, it is ultimately a good predictor, and it can be very useful with very small errors. Now, the model using here is a simple code that loops and updates iteratively to stay true if a force was applied and charts the data. Now, the principle being here shown is the principle of inertia, that an object in motion stays in motion unless a force is applied upon it, and since there's no force being applied, it thus demonstrates a constant velocity. Now here, the experiment is explained such as this. A user pushes/rolls a marker over round objects and records a video. Doing so, we identify the system as the marker and the surroundings as everything else. Taking this video, we can then analyze it in this application tracker and get an average velocity and use that as the base velocity in the code model. Finally, we then chart the two data points, the two data sets, and see how well the model depicted reality. In the process, we use these three formulas in the code. We use Fnet equals ma to demonstrate if a force is applied. However, since no force is applied, this equals 0, which means acceleration is equal to 0, which means this right here, this term cancels, leaving velocity as constant. And as velocity is constant, that causes this to be a simple linear slope equation. Here we have the code. Up here is the initial conditions, with the top one being the position and the bottom one being the velocity. Down here, we see the loop that loops for a second, and right here we see that it would update if there was acceleration. However, there's no acceleration, and thus the velocity is constant, position is linear, as shown in the chart right here. Next slide is the tracker. Similarly, you can see very well that the X is very similar already. However, we'll chart them both later on the same graph, and down here are the data points. Now, this is the chart comparing the two, with the blue being the computational and orange being the real-life data in tracker. Now, here we can see that it's more or less pretty similar. There's a very few small areas right here as we get away from the 2 points used to calculate the average slope. However, it doesn't change that overall it is very quite accurate, and thus we can establish computational model's reliability. Now, what if we flip the axis? Would it still remain reliable? Yes, it would still remain reliable. However, the focus would then change, as we are now looking at velocity constant in the y direction instead of the x. So while the reliability would still be the same, the focus would be a little bit different. Overall, though, the idea of velocity being constant in a direction with no force remains the same. Now, how can we establish that? Well, what is making this up? It's the net force, right? Well, we have gravity and we have normal force, and those two are canceling out from gravity going down and normal force going up. Now, depicted in the little kind of jaggedness of it too is the fact that friction, while very negligible due to the Shoreham type frame, is still there. It's just very small due to its limited chance for impact. Now, in this experiment, there are a couple possible sources of human error. Number one is interruptions in the surroundings, thus affecting the system. However, the data was still linear, and in the process of experimenting, none of the experimenters noticed any possible of that, and thus this is we can confidently say that this did not happen. Additionally, in the tracker analysis, now we humans are the ones making the marking points on the tracker, and thus as shown in actually the Y chart earlier, it was a little jagged, and thus that shows that it is possible to get a little wacky data due to humans being pointed. However, as the point of this was the X component, we during tracking it, we were mostly looking at the chart of X, and seeing that it was linear, we can be rest assured that for the focus of this lab, this was not a major source of error. So, thank you for taking the time to grade this. Thank you for watching this. Have a good day.